Thank you. Thanks for the introduction, and thanks to the organizers for the invitation to speak. So yeah, this is the second talk in this series of lectures about geometrization of periodic local Langlands. What I'm going to discuss today on Friday is part of a joint project with Johannes Anschütz, Juan Esteban Rodriguez Camargo, and Peter Scholze. And it's very much in progress, so I think I try to explain today the part we, I think, understand, and more speculation on Friday. Okay, so as Eugen already explained yesterday, the model for what we are trying to do is the work of Fargue-Scholze. And my task, at least for today, is to discuss what happens on the automorphic side. So let me recall something that Eugen already mentioned yesterday. So if we have G, a reductive group over QP, and let's also fix, so that's the setup of Fargue and Scholze. Let's also fix a prime L different from P. Then what Fargue and Scholze construct is a certain stack, which I will denote, I mean, they call it Bun-G. I will denote it Bun-G Fargue-Scholze to distinguish from another version of Bun-G that will be defined today. And this stack has the property that this receives an open immersion from, well, let me write, SPA-D FP of GQP underline. And what are these, which kind of stacks is that? So in the work of Fargue-Scholze, these are defined as V stacks. So stacks on the category of perfectoid spaces in characteristic P endowed with a V topology. But more recently in the work of Scholze on the motivic version of this geometrization, Scholze works in a slightly different setup, namely he works with arc stacks. So functors on like, sheaves on the category of perfectoid Tate rings in characteristic P with the arc topology. So a morphism A to B of perfectoid Tate ring is an arc over if the induced morphism on Berkovich spectra is surjective. Okay, so that's a variant of the notion of V-stack, where some of you only consider partially proper objects, but all the objects in almost all the objects involved in this geometrization are partially proper, so you don't lose anything by doing this. And so okay, so what are, like, this is just a classifying stack over FP of the arc stack associated to the topological group GQP. So GQP is a locally profiled group, and I just look at the functor which sends A, perfectoid ring, to continuous functions on the Berkovich spectrum valued in this topological group GQP. And then this one, to define it, so it's a moduli stack of G bundles on families of Fargue-Fontaine curves. So the key input is being able to, so it's a moduli stack of G bundles on the Fargue-Fontaine curve. So it's a functor which sends A, again a perfectoid ring, in characteristic P to the groupoid of G bundles on the relative Fargue-Fontaine curve associated to A for the local field QP. All right. And so this morphism, maybe, let me give it a name. So I1 So I1 corresponds to the trivial G bundle on these relative Fargue-Fontaine curves. So basically there are two claims here that the automorphism group of the trivial G bundle on these relative curves is just given by this group object GQP underline, and then that this defines an open immersion. And okay, so you see that for such a thing to be true, if you want the automorphism group of the trivial G bundle to be just this, like the QP points of G, it's really a sign that the notion of families of Fargue-Fontaine curves that you are working with is maybe not a naive notion. So like a priori you could imagine that by analogy with the case of a classical curve, you would define a moduli stack of G, like the Fargue-Fontaine curve, the usual, well, let's say the one that was first defined by Fargue and Fontaine, it lives over SPA QP. So you may try to form the fiber product with, say, a rigid space living over SPA QP and take G bundles on this. But if you do something like this, then the automorphism group of the trivial bundle would just be, like, say, the algebraic or rigid analytic group associated to G, not its group of QP points. And that's not to say that this other construction is not interesting. It is definitely interesting, but it is more, I mean, a variant of this is what Eugen explained to us yesterday. So here we do, like we consider a different notion of families, which is indexed by perfectoid rings in characteristic P. And then we have this behavior that the automorphism group of the trivial G bundle is just GQP. And this is...
It is the case that when you consider A and you consider A plus and A 0, you get the same Fargue-Fontaine curve?
Yeah, this bungee is partially proper.
Okay.
Yes. And yeah, that's why I want to look at it as an arc stack.
I have a question. So yesterday when Eugen was talking, his Fargue-Fontaine curve was always the absolute one, and he just changed the coefficients. Today you are putting the coefficients into the base of the curve.
Yes, exactly. So it's
why is there this?
I mean, it's like arithmetic versus geometric families, and like he's moving the coefficients to define this stack of Fargue-Gamma modules.
But isn't the goal to connect what you are doing with what he's doing in the end by some function?
Yeah, well, yes. I'm only working. I mean, I will only be defining objects on the automorphic side. He was looking at the spectral side, and so yeah, maybe it will be more clear later.
So are the two notions related by Cartier duality?
No. G is not necessarily a torus. It's not necessarily abelian. I mean, in some cases it is some kind of Cartier. But anyway, let's come to this later. So why is it? I mean, the fact that you have this open immersion, in particular, you get a fully faithful functor. So I1 gives a fully faithful Schrick extension along I1. Fully faithful embedding of the derived category of the abelian category of smooth representations of GQP with QL coefficients inside this category of sheaves on bungee, D-list bungee with QL coefficient. Oh, maybe for this to be true, I need to base change from FP to FP bar. So, yeah. Otherwise, I always get, on this classifying stack, I always get contributions from the étal side of SPA FP. Okay, so somehow we have embedded representation, smooth representation theory of GQP inside a sheaf theory on bungee, and then we can use a lot more structures that are available there, like Hecke operators, to say something about smooth representations. That's basically the philosophy. And so the motivating question for today is what about L equals P? And there maybe I should first say that in the work of Fargue-Scholze, there is no need to restrict yourself to QL coefficients. There is also a version with ZL coefficients, in particular mod L, for example. And of course, in the periodic case, you could also wonder about mod P or integral or QP version of this. And I will only discuss the case of QP coefficients, so to say. from our geometric perspective, some of the case of, like the integral theory or the case of mod p coefficients, for example, it's I think much harder to get, and this is something we don't fully understand yet. It's maybe a bit counterintuitive because historically, like p-adic Langlands for GL2 was first understood in the mod p case and only later in the Banach or locally analytic case. But in our framework, it's actually the opposite is happening, and it's related to the fact that integral p-adic Hodge theory is harder than rational p-adic Hodge theory in a precise sense.
But we are writing a paper with Joaquin that explains that you should start with locally analytic also for the classical class.
Okay, very good. Then I think we all agree. Like this unitary Banach case, someone asked yesterday, what about unitary Banach representation? Same question could be asked in Fargue-Scholze, so you could also look at adic Banach representations, but there it's a bit artificial. It's more or less just the limit of powers of, like, you have this category modulo L to the n for all n, and you can take some more limit and then some kind of isogeny category. And I think this same should, if you care about the Banach case, periodically you should probably do the same thing once you have defined everything with torsion coefficients. All right. And so the basic problem one has is that if we try to do QP coefficients instead is, well, first you need to have a good six-functor formalism like this D list with QL coefficients. You need something like this with QP coefficients. And, well, there are some candidates for this. But we also saw that with QP coefficients, there are at least two categories of representations you can consider. Smooth representations and locally analytic representations. And maybe you care about both of them and some of the compatibility between Langlands correspondences for them. And in this setting of arc stacks, in this geometric framework, what you see is this GQP incarnated just as this arc stack is just only remembering like GQP as a topological group. But the theory of locally analytic representations, you are using more about GQP. You are using the structure of a p-adic Lie group. So it's not clear how to speak about locally analytic representations just in terms of this geometric object. But even if you could, then you could also wonder about the relation with smooth representation. So you would have to change your sheaf theory. You would have maybe one classifying stack, and then you have to change the sheaf theory you are using. And we would rather like to have maybe just one sheaf theory and then different geometric objects, different incarnations of the classifying stack, corresponding to different kind of representations. And this was, for classifying stacks, this was already clarified by the work of Rodriguez Jacinto and Rodriguez Camargo. That was mentioned by Eugen yesterday. So what they show is you can define a derived and solid variant version of smooth as locally analytic representations of GQP or any p-adic Lie group as solid quasi-coherent sheaves on unspec QP solid mod GQP smooth or the classifying stack for the locally analytic version. So these are analytic stacks in the sense of Clausen and Scholze. I will say a bit more about this QP solid later today. And what are they? Well, these are defined as, like, okay, G is not necessarily, I mean, in this case, it's not compact, so it's defined as, like, this object is not affine, but it's like a colimit over, like, compact open subspaces of locally constant functions on K with QP coefficients. Oh, sorry, forgot to write unspec of this. And there you do the same with locally analytic functions instead. So these are like group objects in the category of analytic stacks. And what they show is that you can consider quasi-coherent sheaves on these stacks, and this gives you kind of generalization of the notion of smooth or with QP coefficients or locally analytic representations of GQP. And so this is an indication that maybe we should redefine our Bun-G as some kind of analytic stack and hope that in like maybe there will be like two versions of Bun-G, and one of them will give us smooth and the other one will like see locally analytic representations. All right, so to achieve this, you need to develop, I mean, as I say, to define some objects in the world of analytic stacks. And I want to start with some general discussions of something that we call Gelfand stacks. And this part is also joined with Guido Bosco. So we don't want to, like this category of analytic stacks is very big. It contains many examples of geometric objects which have nothing to do with p-adic analytic geometry. And so we want a variant of the notion of analytic stacks. Which is, I would say, like better adapted to doing p-adic analytic geometry. And right, so without like giving full details, let me just maybe first briefly recall that this category of analytic stacks is defined in two steps. So first, Clausen and Scholze define the notion of an analytic ring, so which roughly you can think as a topological ring plus some notion of a subcategory of complete, so a topological ring, let's say A, plus a subcategory of complete A modules inside the derived category of all inside the category of topological A modules. So that's somewhat, well, everything is assumed to be commutative, and that's some kind of topological enhancement of the usual notion of a commutative ring. And then you somewhat glue for a certain topology, so you define analytic stack. They will be sheaves on, so if I denote by an ring the category of all analytic rings, and I take the opposite category, and you need to define a certain Grothendieck topology there, and this is handled with so-called Schrick topology, which I also won't define precisely, but again, very roughly speaking, it's something like finest topology for which you have descent of these categories of complete modules. And there are six operations you can define on them. So in particular, definition is made in such a way that if you have an analytic stack, X, then you get associated to it a certain category of quasi-coherent sheaves. On X, together with a six-functor formalism, which, if X was affine, so corresponds to an analytic ring, is basically this, the derived category of this category of complete A modules. Is it okay? Can you see it, or is it too?
When you pull it down, we'll see it.
Yes, but okay. And so, yeah, basically we want we'll keep working with the same topology, but we want to restrict the category of analytic rings we consider in this theory of Gelfand stacks. So let me maybe for this first give one example of which already appeared on the board of analytic ring is QP solid. So that's a solid. Analytic ring structure on QP. So inside, well, maybe I should write QP underline. This is a condensed ring attached to QP with its natural topology. And yeah, very quickly I will just drop this kind of symbols. I will never underline anymore. And so that's supposed to be an analytic ring structure on this condensed ring. And so this is given by specifying a certain subcategory solid QP of the category of all condensed QP modules. And, well, okay, like you basically, it's just induced from this. So it's just a category of QP modules in solid abelian groups. And this is this as an abelian category. It has a simple structure. It has one compact projective generator, which is given by a product of copies of ZP, indexed by the natural numbers, with P inverted. So that somehow completely determines this category as an abelian category. It agrees with the modules of an endomorphism ring of this object. But, okay, in particular, as the claim that this defines an analytic ring structures, this is a category which is stable under limits, co-limits, and extensions inside the category of all condensed QP modules. And it also contains p-adic Banach spaces, but also anything you can build from them by taking limits, like Fréchet spaces, for example, or co-limits. Right, okay. And more generally, know if A is a solid QP algebra. I can always consider the induced, what is called the induced analytic ring structure from QP solid. And, well, basically this is defined by the condition that mod A, this category of complete modules for this analytic ring structure inside all condensed A modules, is given by, again, just A modules in solid QP. So that's why, like, the condition of being complete is just induced from, it just means that you have some A module. When you see it as a QP module, it is solid. Okay, and so I'm not managing my boards very well. Okay, never mind. So in our work, we will always just consider induced analytic. Everything will be over QP solid. We do p-adic geometry, non-Archimedean geometry, and all the analytic ring structures we will consider will always be induced from QP solid. So that makes life technically quite simpler, and it's kind of related to this passing from general V stacks to just arc stacks. So restricting to partially proper objects. Okay, but so the kind of restrictions we want to put is, I mean, this one is some sort of restriction, but we also now want to put some restriction on which kind of solid QP algebras we consider. And so here I will have to be a bit quick. So the claim is that let A be a solid QP algebra. One can define for any positive real numbers R, a certain condensed subset denoted A less than R inside A, formed intuitively by elements of norm less than R. So these are supposed to be condensed sets, but if I just look at the underlying sets, how is this defined inside the underlying set of A? Well, if I give myself F in A star, it's the same as giving myself, it corresponds to giving myself a morphism from the polynomial algebra in one variable to A, which sends T to this element F. And then the condition of being of norm less than R is a condition that this means that this extends to QPT less or equal to R, which is the ring of over-convergent functions on the disk of radius R. And then you have...
They are over-convergent on the disk of radius or they are convergent on the disk of radius?
Over-convergent.
So you converge more than R.
Yeah, you complain that my notation is not so good. That's the notation we use in the paper, sorry. So I will stick to it. But yeah, it's supposed to mean over-conversion. Right, and then to really define a condensed subset, you have to do this in define this in families. So for any light profound set, you need to really find a version of this condition, which makes sense. So in general, it's just a subset, but when R is 1, it's in fact a subring. And say again?
The extension to the over-convergent ring is unique?
Yeah, it is unique because this is an idempotent algebra over QP, over the polynomial algebra with a solid induced analytic ring structure. So yeah, it's this extension, if it exists, it's necessarily unique. So it's a problem. Okay, so for A as above, solid QP algebra, we then say that A is bounded. So that's a notion which is due to Juan Esteban Rodriguez Camargo. If A identifies with just what you get by inverting P inside this subring of, so to say, power-bounded elements. And we say that A is Gelfand if, well, first of all, A is bounded. And it's a uniform completion, which is defined to be, so you take the part where power-bounded part, and you take a p-adic completion, and then invert P. And you want that this is a Banach QP algebra. So this, at least the notion of bounded ring is, you should think to it as, if we work with, in the analogy with Heuer theory of adic spaces, if we work with all adic spaces, we not only see rigid analytic varieties, but we also see schemes or formal schemes. And the way you distinguish between these two types of examples of adic spaces is that rigid analytic spaces are Tate. So they are glued out of Heuer rings for which you have a topologically nilpotent unit. But this is not the case for schemes or formal schemes. And this condition of bounded is some sort of generalization of this notion of a Tate Heuer ring, so to say. Well, this notion of being Gelfand is also one. And so if some examples of these notions are, so Banach QP algebras.
Sure, could I just quickly ask, the second condition equivalent to demanding that A less than or equal to 1 mod P be discrete?
Yes, that's the same thing.
Okay.
Yeah. Right, and maybe, yeah, thanks for the remark. So Banach QP algebras are Gelfand. Oops. But this category is also stable under all colimits in solid QP algebras, so also colimits of such. So typically the rings of functions on affinoid rigid spaces or affinoid dagger rigid spaces, like over-convergent functions in the sense of grosse Klöner, would be example of Gelfand rings. So, but like non-examples would be something like, well, this polynomial algebra is not Gelfand because it's already not bounded. The element T is unbounded there. Well, if you look at the definition, there is no way you can extend to some Tate algebra of positive radius. And so that's good because this is maybe the kind of examples coming from schemes that we want to exclude. But also something like this power series ring in one variable with P inverted, like something like with n spec of which would be something like a bounded open disk. This is also not, this one is bounded, but it's not Gelfand. So that's the kind of examples you also exclude by imposing this condition. Because if you go mod P, using this equivalent characterization, mod P, you get FP double bracket T with a T adic topology. That's not this.
Excuse me?
Yes.
In condition 2, what is before the equal sign A to the, I cannot read that. Before the sign.
It's a U.
I think that's the definition.
It's a definition.
Okay, it's a definition, I think.
So it's what we call uniform completion. So I think you don't lose.
Sorry, can I ask a question? Is it correct that all the conditions only depend on pi 0 of A?
Yes, that's right. Yeah, so you don't lose, I think, too much by just assuming that you are working with the category of generated under colimits by Banach QP algebras in all solid QP algebras. Yeah, so if you want, that's a way to think about this category of Gelfand rings.
Is derived or not?
Yeah, I wanted to gloss over this point. To set up the theory properly, you have to do everything animated. And I think that's, but I just ignore this. But yeah, you're right that I should really work, we do everything animated. Or maybe just to set up some more notation, let me remark that if A is bounded, I think Juan Esteban's motivation for introducing this notion was that then you can look at R equals 0 is allowed, and that's what you call the dagger nil radical. And the point is that if it's an ideal of A, if A is bounded, and it's called the dagger nil radical. So that's bigger than the usual nil radical, and we will see later where it appears.
Can you repeat the ZP double bracket T 1 over P? Which topology are you putting?
PT and ZPT.
So even though it's not a topological ring, you can endow it with a structure of a.
You can undo it as
an analytic ring, even though it's not a topological ring.
All right. So let me know. Okay, I have to give the definition of Gelfand stack. So a Gelfand stack will basically be like a version of analytic stacks, but for this more restricted category of test objects. So it's a sheaf on I forgot to give my notation. So Gelfand ring is just a notation I use for the category of Gelfand rings over QP. Is a sheaf on the category of Gelfand rings for the for the Schraen topology, but in this case, because my topology, my analytic ring structures are always induced from QP solid, the Schraen topology just reduces to the descendable topology in the sense of Achille-Mathieu. Maybe I should write op. And here I should really put some quotation marks around the definition because, well, first of all, I did not really say which kind of sheaves we consider. So like the official definition, you consider sheaves of anima. And then there is a question of whether you want to work with sheaves or hypersheaves. And the actual definition is in something in between. Sheaves is not enough, but if you work with all hypersheaves, you would lose this descent of complete modules. And so Schraen and Scholze have some kind of intermediate condition between sheaves and hypersheaves that should be put here as well. So yeah, maybe I don't write this. And then the other thing is that to make the theory better behaved, we impose further restrictions on. No, we impose some kind of finite dimensionality assumptions. And also some separability assumption on our Gelfand rings. But maybe I don't want to enter here again into the precise definitions, but maybe just stress what the main consequence of these more restrictive conditions is that this leads to the following proposition that, and let me just say orally that from now on, even though I keep my notation here, I will always assume that the Gelfand rings I work with satisfy these assumptions. Okay, so.
Arthur-César, just a moment. In the descendable topology, what should descend? What do I assume in descent?
I mean that I consider the covers I want to consider are descendable covers. It means that you have morphism A to B of Gelfand rings, and you want that A belongs to the subcategory of dA generated by dB under finite limits and retracts. So you can write A as like a finite limit or retract of a complex of B modules. Like typically, like if you have some analytic cover, like the rational localizations, by writing down the such complex, you see that you get something decent.
Is there a categorical characterization of like this class of math in this analytic context?
Of this class of?
Of this class of math.
Yes, but let me not discuss this.
How does this compare to this Schraen topology?
That's sorry, I should maybe have said it more clearly. A Schraen cover, if the of analytic rings, if the analytic ring structure on the target is induced from the source, is just a descendable cover, and that's everything is induced from QP solid in this talk. Okay, so the consequence of these extra assumptions is basically that we can work with different class of rings. We can even further restrict them. So if F is a Gelfand ring with these extra conditions, then there exists a descendable cover A to B, where B is nil, what we call nil perfectoid, which means that when you mod out the dagger nil radical, something I will usually just denote B bar. This is a perfectly Tate ring, not just. So it's a perfectly Tate ring. In this case, it happens that this is also then the same as the uniform completion. That's a stronger condition. And you can even ensure that B bar is strictly totally disconnected in the sense of the perfectoid series. So the Berkovich spectrum is profinite set, and the residue fields are algebraically closed.
Sorry, are you saying DU and B bar are the same?
Yes, in this case, like you always have an injective map like this, but then this one is already, if I assume it to be perfectoid, it's already uniformly complete. It's already uniform. Wait, sorry.
This is Juan Esteban's definition of neo-perfectoid. This neo-perfectoid, is this from Juan Esteban's first? This from,
So what does strictly totally disconnected in this context mean exactly?
So it's just the usual notion for a perfectoid ring. It means that the Berkovich spectrum is profinite, and the residue fields are complete, algebraically closed. Okay, so let me now give examples of Gelfand stacks. Well, first, maybe just more or less to just set up the notation. If A is a Gelfand ring, we'll denote by G spec of R the functor which sends A Gelfand to morphism from R to A, and this is a Gelfand stack. So these are the affine objects. The second thing I want to mention is that there is a fully faithful functor from the category of partially proper rigid spaces inside the category of Gelfand stacks. So you can be even more general. You can more generally, you have a fully faithful functor from dagger rigid spaces, or even for some, for the category of Berkovich spaces over QP. That's over QP. And so, here there are maybe two claims. First, that there is a well-defined functor like this, which amounts to checking that analytic covers give rise to descendable covers, and then that this is fully faithful. But so in particular, like the usual analytic rigid geometry is kind of embedded inside the theory of Gelfand stacks. And as an example, well, if you take the analytic affine line over QP, then as a Gelfand stack, it's simply the functor which sends A to the underlying set. Right, so you may a priori think that this is represented by spec of the polynomial ring in one variable, but this is not an example of a Gelfand ring. So like this functor is not represented by an affine, by a quasi-compact object in Gelfand stacks. All right, so the third example is coming from the theory of the RAM stacks.
Yes.
So just to kind of check, so we can see your burden thickening to rigid spaces in Gelfand stacks.
Yes.
And maybe I should have, I should have pointed out something about this. Why did I want to state this proposition upstairs? You see that this forms a basis for the topology of this category of nil perfectoid rings, even strictly totally disconnected ones. And so to set up my definition of Gelfand stack, I could actually have used just the notion of a nil perfectoid ring. And if you put things this way, you see that the theory of Gelfand stacks is really close to the theory of arc stacks. The difference is that your test objects are not just perfectoid rings, but some kind of geometrically some kind of over-convergent secondings of perfectoid spaces. And that will be exactly, in some sense, the minimal thing you need to make sense of something like GQP locally analytic. The advantage of defining Gelfand stacks as I did is that maybe it makes more clear why you have a functor like this from rigid spaces to Gelfand stack. Okay, so well, the issue is then you have to consider non-induced analytic ring structures. But yes, I mean, I think Clausen and Scholze define fully. I don't know. Is it known to be fully faithful? Yeah. Okay. Yeah, there is a functor, co-limit preserving functor from adic spaces towards the category of analytic stacks. Yeah. Okay. An interesting examples come from the theory of the Ram stacks, and here the observation is you have a restriction functor from certainly perfectoid rings are examples of Gelfand rings because they are Banach QP algebras. And so you have a restriction functor from Gelfand stacks to arc stacks over QP, over the arc stack of QP, which is just, yeah, as I wrote, restriction from restricting a functor which is defined on all Gelfand rings to perfectoid rings over QP. And this functor has both a left and right adjoint. And the right adjoint is what we call the de Ram stack functor. So it's a functor which goes from arc stacks over QP to Gelfand stacks. So slightly surprisingly, you can define some notion of de Ram stack even for this very, like this notion of this de Ram stack is some analytic de Ram stack. It's a very topological notion. It makes sense for any arc stack. And so explicitly, if X is on arc stack over QP, you have a description of functor of points at least on nil perfectoid ring. So X de Ram of A, for A which is nil perfectoid, is what you get by evaluating on the uniform completion, which is also the dagger reduction. So this formula is reminiscent of the way you define the algebraic de Ram stack by taking the quotient by the nil radical. And here, well, the claim is that when you restrict to nil perfectoid test objects, you don't need to, like it's really, you don't need any, no sheafification is necessary. I mean, this involves proving some results about if you have a arc cover of, yeah, you need to prove some statements like arc cover of perfectoid rings with some assumption on the finite chronological dimension assumption on the Berkovich space give rise to descendable covers. This is the kind of statement you need to
check. So this coincides with Hernandez-one's original formula?
Yes, so let me come to this. So e.g., maybe two examples. If X is, if X is of the form T underline for T topological space, where T is like, this is a notation I've been using at the beginning already in a particular case, then in this case X de Ram is what is called is a Betti stack, base change to QP solid of Clausen and Scholze. But if X is a partially proper rigid space, and then I should maybe introduce one more notation, which is that if X is a Gelfand stack, I will also use the notation X de Ram for, okay, so this is this functor is something I will denote with a diamond because it's this restriction functor is really some version of the diamond functor. And then the de Ram stack of a Gelfand stack will be by definition just what you get by first applying this diamond functor and then taking the de Ram stack. So in particular, it comes equipped with a natural map from X by adjunction. And the claim is that for a partially proper rigid space, this de Ram stack is just the morphism from X is surjective, and you get just the quotient by the over-convergent diagonal. And so using this, you can see that it agrees with Juan Esteban construction in this situation at least, and computes the RAM, over-convergent the RAM cohomology in the smooth case, which justifies the name for this construction.
And for this, you don't need that X is smooth?
For this, you don't, no. But, yeah.
So if you can drop this partially proper assumption, you think you can recover the original?
This works also for dagger rigid spaces. Yeah. And maybe I should, like the corresponding, if you take a dagger rigid space, the arc stack, the diamond associated to it is just the same as for its uniform completion. So like the Durham stack of the affinoid disk of radius 1 and the over-convergent disk of radius 1 are just isomorphic. And so using this statement for dagger rigid spaces, you deduce that for the affinoid disk, what this Durham stack is computing is just over-convergent Durham cohomology automatically. All right. And last example is if G is a rigid analytic group over QP. This example is in some sense just a special case of the previous example. For example, take my reductive group G and take its analytification. Then, inside the diamond of G, I have the set of locally profinite set of its QP points. And when I pass to the Durham stacks, this gives me morphisms from GQP smooth as previously defined, which is also the same as this Betti stack, inside G Durham, which I will call is G by definition G diamond Durham. And this GQPLA is actually the same as the fiber product of GQP smooth with G over G Durham. G is a group object, so in fact this Durham stack you can describe just as G modulo G dagger, which is like G spec of over-convergent function around 1. And so basically I think this formula is reasonably intuitive because it's basically saying that you are taking some kind of, the GQPLA is some kind of over-convergent neighborhood of this locally profinite set inside this rigid analytic group. Okay, and this formula will be useful in a moment. All right, I think that's all I wanted to say about Gelfand stacks. And now let me fulfill what I promised and define this new version of Bungie. So we will define Bungie as a Gelfand stack. And then sheaf theory, then because it's a Gelfand stack, we have a natural sheaf theory to use on it, which is just quasi-coherent sheaves. So there will be no adic sheaves anymore. And so this will be, because this by design lives over QP, solid, this category of sheaves, quasi-coherent sheaves on this new Bungie will be a QP linear category. So that's a version with QP coefficient.
In the previous sentence, Anderson, is GQP LA sub, you said it should be a part of GQP? It subjects to GQP smooth. No.
GQPLA subject to GQP smooth, yes. G subjects onto G Durham as well. Like the fiber is just given by like the over-convergent neighborhood of 1 inside what I wrote over there. Okay, and we saw that the subcategory of nil perfected rings form a basis. So if I want to define this Bungie, it's enough to specify what it does on nil perfected rings. And as in the work of Fargue-Scholze, you see that the key is to be able to define a notion of families of Fargue-Fontaine curves, and then the definition is the obvious one. And so let me give straight away the definition. So let A be nil perfectoid ring. So always over QP. Define the Fargue-Fontaine curve associated to A as the push-out of the Fargue-Fontaine curve associated to uniform completion or dagger reduction, as you like, of this. Maybe I should put a flat over G spec A bar flat. Sorry, G spec A bar with G spec A. So what I'm using here is that A bar, note that A bar is, by assumption, by definition of being nil perfectoid, this is a perfectoid ring, a tape perfectoid ring over QP. So if I tilt it, I get a perfectoid ring in characteristic P. I already know what the Fargue-Fontaine curve over perfectoid base is. And there is also a natural map from G spec A bar inside Fargue-Fontaine A bar flat, because untilts of a perfectoid ring in characteristic P give rise to such Cartier divisors on the Fargue-Fontaine curve. But I also have a natural map from G spec A bar to G spec A. And so basically I'm taking the usual perfectoid Fargue-Fontaine curve over the dagger reduction, and I'm doing just some kind of dagger nil thickening along this preferred Cartier divisor that I have. So this definition is, you have to be a bit careful in which category you take this push out. It's maybe a small lie, but it also may seem very ad hoc. But in fact, you can really define it. This is just to be quick. You can define it by using Witt vectors as you would do for the usual definition of the Fargue-Fontaine curve. What's happening there is that when I take Witt vectors of A, or maybe the power bounded part, it will map to the Witt vectors of this dagger reduced piece. But then it also, the fiber is given by Witt vectors of the diagonal radical, which consists of elements which are infinitely divisible by P. So it's a QP module. And by Gauss components, this just identifies with the product of copies of the diagonal radical. And because everything is done up to Frobenius action, this means that in the end, I'm just taking this dagger thickening along this specific divisor. Right, so this definition, in particular, you get out of it that vector bundles on Fargue-Fontaine A is a fiber product of vector bundles on the Fargue-Fontaine A for the dagger reduction. And the thing for G spec A, and same for perfect complexes. So this makes me realize that I forgot to say that there is a good notion of vector bundles on perfect complexes on Gelfand stacks. They satisfy descent for the descendable topology. So these are like well-defined things. Well, in this case, it just corresponds to finite projective A modules or A bar modules. All right, and so then I can finally define Bun G. So let Bun G, as you can guess, the functor which sends A nil perfectoid to G bundles on Fargue-Fontaine. And now the proposition is that this is a Gelfand stack. And the trivial G bundle defines an open immersions of Gelfand stacks from the classifying stack of GQPLA inside my Bun G. Right, so here this is just short notation for everything is happening over QP, so I just write point for G spec QP. Okay, and maybe I take just 1 minute to say why such a statement is true. So for the first the claim is that this is a Gelfand stack. So this means that I have descent for this construction, the functor sending A to I mean, by Tannakian arguments, you reduce to the case of vector bundles, and you need to see that the functor sending A to vector bundles on Fargue-Fontaine A satisfies the descent for this descendable topology. And by definition, by this formula, a vector bundle on this stack is just obtained by this gluing construction. So you basically need to understand descent on both parts. And for this, it's part of this claim that I made that there is a good notion of vector bundles on Gelfand stacks. And here it's a bit more subtle because you pass to the dagger reduction. And so what you have to use here is that descendable covers of Gelfand rings induce arc covers on uniform completions or on the dagger reduction. And then you use these very strong descent results that we know already for vector bundles on perfectoid Fargue-Fontaine curves due to Kedlaya and Liu. You even have V descent of vector bundles. So that's basically the idea. And then, again, this claim, there are two parts. So first, there is a claim that automorphisms of the trivial G-torsor on these families of Fargue-Fontaine curves is given by GQPLA. But using, again, the push-out description and the formula that is just over there, you can do this, the computation. So follows from push-out description and this formula here. And then finally, there is a claim that this is an open immersion. But again, you can observe that this bungee that you have, it is defined, again, from the push-out definition, it is a pullback of the following diagram. So you have point mod G goes to point mod G de Rham, and then you have the de Rham stack of bungee in the sense that, so recall that this is just the de Rham stack of the associated arc stack. And now you look at the functor of points description and you realize that this is just bungee Fargue-Scholze times SPAC UP de Rham. So this part of my diagram is really just passing to the Rham stacks and like base change to QP and passing to the Rham stacks in what Fargue-Scholze would do. And right, I know that point mod G QP smooth sits inside here as an open substack. This again I deduce from Fargue-Scholze, and then this diagram gives me a pullback. So I deduce that this morphism over there is also an open immersion. Sorry, that was very sketchy, but I should stop here. Sorry.
Another question for the speaker?
Yes, I had a question. On the metal board, when you talk about the restriction pointer from Gelfand stacks to arc stacks, like what is the restriction pointer?
I have a functor which is defined on Gelfand rings over QP, and I only evaluate it on perfectoid rings over QP.
Okay.
I need to check that it's defined or defined as well.
So if I consider bundles, I consider like classical kinship over bungee drum is like smooth representations.
Yes, something like this. I mean, you see that you have two objects that you can work with, bungee and it's the Rham stack, which is just something you can directly, for defining bungee de Rham, you can actually just do it using the arc stack defined in Fargue-Scholze. And yes, this one, the trivial bundle here would correspond to, so you can complete, that's what I was using without writing. You have this open immersions of point mod GQP smooth inside, and then you have, again, pullback diagram like this. Well, I never know how to write them. And yes, so this, I would say, like taking quasi-coherent sheaves on this bungee de Rham is like doing a versions of smooth Fargue-Scholze, but with PID coefficients. So this one is really the locally analytic version.
Is that expected if I take isomorphs of QP bar with QL bar? Like, can you prove the two boundary has the same?
Yeah, so Scholze has this motivic version of Fargue-Scholze, which works even with Z1 over P coefficients. And defined using the theory of motives, as discussed by Timo and Alberto and Veronica. And yeah, so this should be somehow a particular realization of this motivic version that Scholze is considering. So yeah, what's happening on this part of the diagram is, in principle, you can just deduce everything from the motivic version, which I think is a way of answering your question.
Okay. Sorry, for the last diagram, the vertical arrows are in this direction or the other direction?
No, it's this direction. So it means that, say you have a G bundle on Fargue-Fontaine A, you have a morphism by construction from G spec A to Fargue-Fontaine A, you can pull back along the. So what is this doing? I was also too quick. It's just pull back along of G bundles along the morphism from G spec A to Fargue-Fontaine A. But the functor which sends A to G bundles on G spec A is by definition the classifying stack of G. Right, up to the fact that this is really seen as a Gelfand stack, so implicitly I'm always taking some kind of identification.
Is there a good notion of Gelfand stack also in characteristic P, like nil perfectoid rings?
Yes, but that's what I said in the introduction. I think setting up the theory is more well. For the notion of nil perfectoid rings, I think you can define. But yeah, so the correct definition there should also be a notion of relative Fargue-Fontaine curve, and then it's not just simply given by a push out. And what I said orally, when you take Witt vectors, I was using the fact that my pseudo-uniformizer is P to identify the Witt vectors of the diagonal radical with just a product of copies of the diagonal radical. But this would fail if I was doing nil perfectoid ring over some Laurent series ring in characteristic.
But the result would always be some nil perfectoid thickening of the usual Fargue-Fontaine curve of the dagger reduction?
Yes, but not just supported on this.
Not supported at infinity.
No. Okay, so let's sign the paper.